One of the first problems we looked at in class today was what I call the fence problem. And so I'm going to walk through my thinking that I would have used to solve this. And some of you did a great job explaining this in class this week. So you could just also refer back to your own version of the problem. But in case you weren't in class or you still have some questions, hopefully this video can give you some guidance. So this is a pretty traditional optimization problem. We have a rectangular area of land. We're told that it's 3,200 square feet. It's in a rectangle. We have three sides of it fenced in with fence that's going to cost $2 per square foot, and then a special wall on the fourth side that will cost $6 per square foot. So I'm going to color code the three sides for $2 in pink and the fourth side with $6 in blue. And we want to find the dimensions that minimize the cost. And we eventually want to come up with the dimensions and the minimum cost. So I'm just making sure I have what I'm trying to answer. Now, that means eventually I need to come up with a cost formula. So in the end, I need a cost formula. But I'm not necessarily going to be able to get directly there. I always like to start by drawing myself a picture. So in this case, I have a rectangle. And rectangles have four sides. And if this is side X, this is also side X. And if this is side Y, then this is also side Y. Now, we're given this extra piece of information that said three sides will cost $2 per square foot, and the fourth side will cost $6 per square foot. So we're going to imagine that this is this blue side right here, that's my $6 per square foot side. And then these three right here, those are my $2 per square foot sides. And then I'm also given an area of 3,200 square feet, pardon me. So I have an area. So I do know the area of this rectangle could be found by taking the length of X and timesing it by Y. And I also know that area needs to be 3,200 square feet. So I have this equation, and I'm going to leave that alone for now. Now I want to go and think about the cost formula. So I'm minimizing the cost of fencing. Fencing goes around the outside of an object, which means I'm creating my cost formula using perimeter. Now, the perimeter of this object, or this fence, perimeter, would be, X plus X plus Y plus Y. And I wrote it this way because these three sides that I've sort of bracketed in pink, they're my $2 per square foot side. And this extra Y here, that's my $6 per square foot side. So when I go to write my cost function, so I'm going to do C for cost, I have X plus Y costing $2 per square foot. So it's like that total length times 2. And then that gets added to that Y length, which is times the cost of 6. And so this would get me my sort of total cost for fencing that rectangle. There's a few things that I'm going to need to work with here. One, I can obviously combine some like terms. So I'm going to go through and do that first before I worry about the fact that I have X's and Y's going on. So if I notice, I could distribute that 2 throughout. So I have 2x plus 2x plus 2y plus 6y. And then I'm going to group my x terms and I'm going to group my y terms. So I end up with 4x plus 8y. Now I need to worry about the fact I have two different variables here because I have x and I have y, but I want to make cost a function of x. And so because of this, we're going to go up to what we often refer to as our sort of constraint formula. And this is sort of creating the limits on our function we want to minimize or maximize. Now, in this case, I need to rewrite this formula so that I've solved for one of my two variables. It really doesn't matter which one you solve for. Since I made this a function of x, I'm going to rewrite this as a y equals equation. So y equals 3,200 divided by x. Or I could think of that as 3,200 times x to the negative 1. And so this value is equal to y. So I'm going to go down here, and in my original function, I'm going to replace y, my cost function, with that rewritten expression. So I end up with a cost equation of c of x equals 4x plus 8 times 3,200 x to the negative 1. And I can simplify this a little. So I'm going to do 4x plus, and it ends up being 25,600 x to the negative 1. So this function here would find me my cost. So we have the cost function. But we're not done. We were asked to minimize. Well, minimums on functions occur when my derivative is equal to 0 or undefined. I actually know for sure this derivative is going to be undefined at 0 because x in the original function is undefined at 0. But x can't be 0 because if x was 0, my rectangular fence wouldn't exist. So I do have a restricted domain. My domain is basically all positive numbers. There's no max value here, but it can't be 0. So I'm going to now find my derivative because I need to figure out where c prime of x equals 0 or is undefined. And that's part of why I rewrote that one piece as x to the negative 1, because I now basically have a series of power terms which I can easily take the derivative of. So the derivative of 4x would be 4. The derivative of the second term would be minus 25,600 x to the negative 2. And I need to figure out where this derivative equals 0. So I'm going to plug 0 in for c prime of x. And I want to solve. And I'm going to actually go through and show you how to solve this algebraically. However, if you wanted to use a graphing calculator to solve, that is acceptable as long as you tell me the equation you are solving. So here, I'm going to add this term to my other side. So I end up with it as a positive, actually. And I'm going to also rewrite that to be over x squared, and there's a reason. Because this allows me to sort of more clearly see what I need to do. I need to get that x squared out of the denominator. So I'm going to multiply both sides by x squared. So I get 4x squared over here. And then I would divide out the 4. So I end up with 6,400 equals x squared. And the last step would be then to take the square root of both sides. So x could be positive or negative 80. But we're going to go back to this domain over here. Because remember, we said that x had to be a positive number. And I got two solutions here. So really, it can't be negative. And so I'm only going to care about one of my critical values, the positive one. So I found a potential critical point. I need to test. So next step, I'm going to test to see if my critical value is a minimum, because that's what I was looking for. So I'm going to use the first derivative test. So to use the first derivative test, I make a little sign chart. So we're describing C prime. 0 is the minimum value. I have 80, and then it keeps going. So if I go back to my derivative, that's C prime, and if I were to plug in a number like 1, I made it easy, 1, I would get 4 minus 25,600. Well, that's going to come out negative. And then if I plug in a number more than 80, I'm going to end up with a positive number, because that 25,600 would be divided by something larger than 4, or it would come out with a quotient larger than 4. I'm saying this wrong. I would get an output in that piece that would be smaller than 4. Therefore, 4 minus that number would get me a positive value. So basically my function, so in knowing the derivative is negative on this interval, it was decreasing, and then it's positive on the second interval, so that would be increasing, and since my function is going decreasing to increasing, it's a minimum. So yep, good, works. Check. Must be a minimum because C prime changes from negative to positive. All right, so now we need to go back to the original question. And what was I actually asked for? And that's why I highlighted it way back here. So I was asked, what dimensions will minimize your cost? State the dimensions and the minimum cost in a complete sentence. Well, I have one dimension. I have the 80. So I actually need to go back and plug some numbers in. So, I need to find dimensions and minimum cost. Basically, answer the question. Well, the area was 3,200, and one of my dimensions was 80, and so I can solve for the other one. So y would be 40. So I know I have an 80 by 40 area, and I'm also asked what is the cost, and so I would go back up. I can go either to this level, or I could go back even to this level up here. I sort of like that level up there. So C of 80, and I'm going to do 40. And it was 4 times 80 plus 8 times 40. And I would get 320 plus 320, which would be $640 as the minimum cost. And it did ask for a sentence. So the minimum cost of fence would be $640 when the rectangle has the dimensions 40 feet by 80 feet with, and we do need to specify because it can't just be either way. Keep in mind that the y value, the 40, was our $6 side, with the special fence along one of the 40 feet sides. And that would be how we would tackle this particular fence problem. I hope that helped, and stay tuned for some more videos on the rest of the problems.